there is a plethora of choice of devices available. How you know which one is better? So to do that, you need to do this calculation. So our tool will go fetch the data sheet. In the background, it will do, all the cup fitting and give you the numbers. If you look at the total EV penetration today in India, it is about 5%. Good morning, everyone. Hi, I am Kaushik. I am Associate Professor at the Department of Electrical Engineering at IISc Bangalore. And I basically work in the area of power electronics, right? And is there anyone here who works in power electronics? Okay. Okay, so the thing is that I think, but I am assuming most of you guys are from circuits, right? Yeah, so for this talk, all you need to know is buck converter. So this is a little bit about our institute. So we are about 500 faculty and 5,000 students, and we are in all areas of engineering and science, and now we also are getting a medical school. So I head this lab. We call it Sustainable Power Electronics Lab. Currently I have about 9 PhD students, 3 MTech students, and 3 project associates. And about 50% of our funding comes from government, and the rest comes from industry. And we work with big guys like Texas Instruments, Delta Electronics. We also work with startups like Arbor Mobility, also mid-range companies like Ethar. So we are essentially into power electronic converter building, right? So mainly the research topic is, on the circuit side. We call it topology, like how the MOSFETs are actually connected, right? It's called topology, and then the switching strategy. And then we have to do some kind of closed loop control. So you need to do some dynamic modeling of the converter. So, and then finally you do design, right? And we also little bit work on the components. So if you look at a power electronic converter, in the base you have this power MOSFETs, which we use like an electric switch, like you use it in digital circuits, either on or off. So we little bit work on that too, and that is what I'm going to discuss today, and not a lot on the circuit side of the things. And in the lab, we are capable of now doing from few hundreds of watt to going to few hundreds of kilowatt. And for all kinds of application, from next generation GPU power supplies at low voltage to fast charging electric vehicles at connecting to medium voltage. So this work is based on 2 of my PhD students. One is graduated working in Delta, and another student is about to graduate. So I think probably all of you know this circuit. This is the buck converter, right? So now I think it is not coming on this, but
that's okay.
That's okay.
That we know basics.
Yeah? Yes.
So
yes.
it's not worth to
Yes. We'll not go through that. So, but what I'm trying to point out here that we have a MOSFET there, and so it is working like a switch. So you have a voltage across it and a current through it, and when the switch is on, it's a short circuit. So voltage is 0, and when the switch is off, current is 0. So if you multiply voltage into current, for ideal switch, there is no loss. But in a real switch, what happens is that when you make this transition, when, say, for example, switch is turning off, current is going from non-zero to 0 value, and the voltage is going from 0 to a high voltage, that time there is going to be an overlap, and that little bump in the VI product or the curve, the area under that curve, is the energy that is being lost during switching. So essentially that energy multiplied by your switching frequency, you repeatedly switch on, switch off. So that gives you the loss, right? And because we are processing power in power electronics, we are sensitive to loss. Now what happens is that if you increase the switching frequency, the size of your components like those inductors, capacitors become small, so you get very compact converter. But you can see that if you increase the switching frequency, your switching loss also increases. So, and even if you are not worried about efficiency, if you let the switching frequency go high, your heat sink or your thermal mass that is required will start becoming big, and overall the converter size will go high. And if you look at in that little triangular bump that I have drawn here, the peak of that triangle is decided by the circuit operating condition, the voltage and the current that is in the working condition of it. But what really matters in that area is that how fast the switching happens, right? So if you increase your switching speed, what will happen is that the base of that triangle will become smaller, and that's how your E on E off will be reduced and you can get higher frequency. So now why we are doing this work, I'll tell you a little bit. So what was happening in power electronics is that till 2010, all the power MOSFETs that we were using were silicon based, right? So if you go at a higher voltage, like where you have a 3-phase power, you go beyond 10 kilowatt or you go around 1000 volts, then people use silicon IGBT, insulated gate bipolar transistor. It's a bipolar device. And at low power, say for example for your phone charger and all of that, you use or single phase power, you use silicon MOSFETs, power silicon MOSFETs, right? So now the thing is, what has happened is from 2010 onwards, we have seen there is a new kind of devices have started coming, and the silicon devices are in competition with them. So if you look at on the IGBT, it is silicon carbide MOSFETs, and they are called so-called wide-bandgap devices because they can block higher voltage. Still the drop is small, and because the drop is small, all the capacitors which decides the switching speed, they are also small. So you get fast switching, or that base of the triangle becomes smaller. Say for example, if you take an IGBT will switch over hundreds of nanoseconds in microsecond. But if you take silicon carbide MOSFET, it switches in tens of nanoseconds. So that means that for the same efficiency or same loss, if you replace silicon IGBT with silicon carbide MOSFET, you should be able to increase the switching frequency by 10 times. So in beginning of 2010, we started getting these devices, and you can slowly see that the voltage rating almost remained the same, but the current rating gradually increased till now. And the silicon carbide MOSFETs are in competition with silicon IGBT at high power, high voltage, and low power, low voltage, it is the gallium nitride which is in competition. Now the gallium nitride started little later, about 2015-16, around that time, and still I think the power has not power GaN HEMTs, what we call high electron mobility transistors, they have not yet stabilized in the market. But you have seen probably in Amazon these smaller chargers, right, for your laptop and phone, which are like 60-watt charger. So compare with silicon will be of this size, but the GaN-based chargers are much smaller, that you must have seen. So that is the technological improvement that is happening there. So now when we started this work, people started asking that, that there were two things that was happening in 2016-17 when we started doing this work. One is that if you try to just simply replace silicon IGBT with silicon carbide MOSFET, circuits does not work. You see a lot of ringing, a lot of EMC issues, and a lot of other problems. And so what people do is they will slow down the switching. Now if you slow down the switching, then if you switch it like IGBT, you don't get that differential improvement that you are looking for by using these devices. So that is one of the problem. Another problem, what happened is that, see, when what I have given you here is a very simplistic picture, and this is what is usually given in the textbooks. It is assuming that, the current and the voltage are linearly going up and down. But in a moment, we will see that it is actually a complex dynamics that takes place, which is really not linear like this. so the estimation is not that straightforward or that simple, right? So now what used to happen is in the IGBT era, with IGBTs it is possible because it is slow, it is possible to do some kind of a scaling based calculation given the datasheet of the IGBT. So a designer will know the specification and also have a datasheet of the IGBT, and then they know how to compute the losses. The same thing goes with silicon MOSFETs, right? The popular thing that people do in industry for the calculation is called gate charge method. So now when people applied those techniques to silicon carbide or gallium nitride HEMTs, it did not work. So your estimation of loss is very important from the design perspective. That decides the key design parameter, your switching frequency, how fast you are going to switch, and also it decides how big your thermal systems are going to be. So that is the the perspective or the background in which this work is being done. Now, okay, so we have seen buck converter. There is a switch and a MOSFET that is used in that. So now the thing is that what we want to do now is we would like to figure out how the voltage and the current changes, current through the device, voltage across the device changes during a switching transition when it is going from on to off or off to on, right? When I say on, I mean that it goes to the ohmic region, and when I say off, it is in the cutoff region, right? It's like a digital circuit, CMOS type of switching. Now the thing is that there are now innumerable number of power electronic converters are there. So the question is that are you going to do your switching study and the estimation for each of those converters, or can you do that in a particular specific converter and extend that idea to all other possible converters, right? And it turns out that this is possible. So if you look at power electronic converters, 99% of the power electronic converters, you will find two N-channel MOSFETs are connected in series like this, right? Think that is your buck converter, N-channel MOSFETs are connected, and then across a stiff DC, and here there is a current port which is an inductive current port there, right? So the thing is that if you actually study this, you can extend your results to 99% of the power electronic converters. That's the basic idea. So now what happens is actually this is what we called half bridge in power electronics. It's called bidirectional half bridge because it can flow power both from here to here and here to here. And actually if you look at this carefully, you will see that when the current is flowing in this direction, when you turn on the top switch, current flows like this, and when you turn it off, current will transfer to the bottom diode. So it acts essentially like a buck converter. And if the current is flowing in this direction, then if you turn on this switch, current flows through this, and if you turn off, it will flow through this diode, right? So now in a bidirectional thing like this, what happens when I want to go from top switch to say the bottom switch, I want to turn on, top I want to turn off, and bottom I want to turn on, then what we typically do is we do not turn it off and turn it on immediately because that could cause a short circuit. So what we do is we go through a dead time. So say for example, first what you do is you are going from top to bottom. So you basically you turn off this switch and let the diode take the current, and then you turn on this switch, then the MOSFET will conduct in the opposite direction, or it will be the reverse conduction of the MOSFET. So now basically when the switching transition happens during dead time, it is always with a switch and diode, right? So that's why we can, so this is just a buck converter, right? So we can just simply study this using one switch and one diode, with a current source here and a voltage source here. And why I say that this inductor can be replaced as a current source, the reason is that this inductor actually current changes in this inductor in the switching period. Current goes high and low, and they say the switching is 10 kilohertz, that means 100 microsecond. But the switching transition that we want to study, that is happening in hundreds of nanoseconds. It's a much smaller time. And in that short period of time, inductor cannot change, current cannot change. Though this is not completely true when we study some of the very high frequency converters where the switching frequency also is very low, very high, and the time period is small. This assumption does not work, but I will not go into that. So essentially, now I have the circuit that where I want to study, the switching transitions or transients. So now I have switched this. I have put the MOSFET here and the diode here. This is my DC source and this is my current. So what happens here is that I have done this because then I can turn on, turn off this FET with respect to the ground instead of studying it the other way. Switch and diode here. So that's one advantage, and another advantage is that you can probe this with high bandwidth single-ended probe, voltage probe. So what we would like to know? What we would like to know is the following: is that we would like to know how long when you turn off, what is the overlap time between them. So there is also ringing. We want to know the frequency of that ringing. There is also overshoot in the voltage. And that overshoot in the voltage can kill the other MOSFET. Okay? So that happens actually in practice when you try to switch it a bit fast, right? So you want to know all of this thing, and particularly from the EMC perspective, you need to know the DVDT, you need to know probably the DIDT, and definitely the ringing frequency. So the whole point is this, that we would like to develop a dynamic model where we will take the data from the datasheet of the MOSFETs and the designer knows the specification, and if you add these two, I should be able to estimate all of this without actually building the circuit. That is the whole idea, right? I should be able to estimate. So now the model of the MOSFET is, this is what all of us study, in device electronics, that this is the drain source, and then you have this Miller cap here, then you have a channel voltage dependent current source here, current sink here, that is the channel current, which is a function of the gate source voltage and the drain source voltage, and then you have a capacitor here which is a function of the drain source voltage, and this is the Miller capacitor, and then you have the gate source capacitor. Right? This is what we know actually, but it turns out that in this problem, this channel current is not that beautiful square law that we learned in our analog electronics classes. And what happens is that actually there are inductances in the terminals. When you take a MOSFET, when you are probing the MOSFET, you are probing only at the terminals of that MOSFET, not the die, the pad where the die is connected, right? So there is a wire there. That wire has inductance, and if you are talking about a current changing in few nanoseconds, 30 or 100 ampere current changing in few nanoseconds, you are going to see a large voltage drop across those inductances. They are typically in nanohenries. We will look at that. And another thing that we have noticed is that every power MOSFET that you see, they put an internal gate resistance so that you just don't short the gate with a high voltage, right? So now the thing is that of course we first try to use this model using the basic square law that we know, but it does not work.
The model is pretty simplified from a loss perspective, because I don't see RDS on, and I don't see RDS on dynamic, and I don't see the hysteresis losses in the output capacitance.
Very good question.
Pretty simplified, because you will totally underestimate losses if you don't take the other things into account.
Correct. I think that's a very important, very good point. See, RDS on we have not taken here because we are not looking at the steady state conduction loss. We are looking at what's happening in the switching. So when the switch turns on fully, then you look at the RDS on and you look at the loss. That is the conduction part of the loss. But here, so I will go back to this circuit. So here what happens is, you actually, when the current flows, you have a loss here. That depends upon the RDS on. right? Because channel is modeled as a resistance.
The output capacitance also
Yes,
has losses.
yes,
They
yes,
are
yes.
relevant in switching.
Yes, of course. That I'm going to discuss because that is what I have taken here. You see,
Okay.
that capacitance I am going to model, right? So the thing is that then, there was a lot of work done on the device literature and a lot of different models have been published. So then we went through that and tried to match with experiment, and then finally we found that for silicon carbide, this model works well. Okay, so you can see this is the channel current as a function of gate source and drain source voltage. So this is 0 when you are below threshold voltage, the FET is cut off, and you can see this is sort of your saturation region where you see that square law here. If I put theta equal to 0, you get the square law here, right? And then this is what the expression is in the ohmic region. And actually, if you go deep into the ohmic region, then you will see like what you are saying, right? You can approximate this as a straight line here, and that straight line is your RDS on, right? So the thing is that what we have, and you can see there are a bunch of coefficients there. So what we did is we took the datasheet numbers and then we did fit a curve on that and found out those coefficients through an optimization problem. So, and then the capacitances, like as you said, those capacitances are also nonlinear, right? They are a function of gate source voltage, the drain source voltage. So that also we took the data from the data sheet and we did some curve fitting. And we found out all the coefficients. The hysteresis of the capacitance, I will talk about that in due course. So now here, what I have put here is, just a comparison of typical silicon IGBT and a silicon carbide MOSFET. I know this is a busy slide, you don't have to see all of that. But what I want you to see here is that if you look at the effective RDS on is very similar, though IGBT is a BJT kind of device. You have, we call it VC SAT, right? It is not really RDS on, but if you compare the resistance, they are very similar, right? They are not very different. So if Infineon is telling us that you can use silicon carbide MOSFET and your losses are going to improve, conduction losses are going to improve, which are RDS on dependent, which may not be accurate, right? But if you see, the other thing is that, but what happens is that this guy has also a anti-parallel diode, the silicon IGBT. Silicon IGBT has an anti-parallel diode, and the BJT cannot conduct in the reverse direction. That MOSFET can conduct. So I'll just tell you two typical applications where this is relevant. So if you use this in a motor drive, which is a big application area as an inverter, in motor drive power factors are poor. You have like 0.8 power factor and things like that. So there the body diode of the IGBT conducts. So there if you use silicon carbide MOSFET and you turn on the MOSFET, instead of its body diode, it will be, the reverse channel will be conducting and you will get a much better performance. But if you are doing this with grid tie inverter, like your solar inverters or your wind inverters and that kind of thing, where almost we operate at unity power factor and that diode does not come into picture. So there you will not get the conduction loss benefit of using silicon carbide with respect to IGBT. But if you look at the output capacitance, you can see that the output, which is related to the switching, you can see that silicon IGBT is much bigger than the silicon carbide MOSFET, right? So the switching speed depends upon these output capacitors, and switching speed is much, is supposed to be much smaller, and that is, you can see almost a decade difference is there, and that's why this guy switches in hundreds of nanosecond and silicon carbide switches in tens of nanosecond. So we did the same thing for also gallium nitride, but here the functions are different, and this is particularly for E-mode GaN, which is commercially relevant. So here also I told no that at lower voltage you have these two players, silicon MOSFET, silicon superjunction MOSFET is today, if you take most of your laptop charger and all of that, it will have silicon superjunction MOSFET in it. So if you take the silicon silicon superjunction MOSFET, so this is what is used today, right, in most of our low power stuff. And this is one of the E mode GaN. You look here, and I will just compare this with this. I will not look into others. It is a busy slide. So you can see here that of course we have a better RDS on here, almost half. So you will get better conduction loss if you replace your superjunction with this. But the biggest the effect is the superjunction has a bad parasitic body diode, which comes with a lot of reverse recovery when you switch, and that leads to huge amount of loss, which limits the switching frequency. But actually there is no diode in gallium nitride FETs because it's a 2D electron gas which carries current, so there is no diode there, right? So you can see that there is no reverse recovery here, and here the reverse recovery is very large. And of course you can also see the the COSS, which is also, I think there is a mistake here. I think this is the one we need to see. So if you see here, this is also large compared to the output capacitor. So okay, so we have modeled the device. Now we have to also model the rest of the circuit. So if you look at the rest of the circuit, what you have is you have a DC bus across these two FETs. Now there are wires or the PCB through which you have connected your DC bus, and then you will have a decoupling capacitor to take the high frequency switching current. But that decoupling capacitor also is going to have ESL, right? And at those frequencies, those ESLs will appear in the circuit. So this LDC represents your the layout, and this is what we call power loop layout, and the power loop the ESL, all those inductors, we have bunched them together here. And then another very interesting thing that we have found is that the PCB, when you do plating, right, with FR4, you get capacitors. But what happened is that before, as you have seen, those capacitors were in thousands of nanofarad, right? But now those capacitors has become in hundreds of nanofarad or smaller than that. And no longer we can neglect the capacitances coming from the PCB. So you need to take them. And sometimes these capacitances actually dominate over the Miller capacitance, right? So anyway, so you need to actually put all these parasitic capacitances along with the model, and then you can actually write down, then it becomes a circuit, solving a circuit, right? So you solve the circuit, and you can figure out how the voltage and current is going to change across the device and find out the loss. Essentially, that is the idea. Now the thing is that how I'm going to get all these capacitances, right? So the thing is that if you actually make the PCB, then you can measure, with what is that called in right? You can measure all those capacitors. We have figured out a simpler method also, experimentally you can measure. So the idea is actually very simple, that if you are measuring this capacitance, right, so what you do is you put a resistance here and you step it, then it is a RC charging, then from there you can find out the capacitance value. But the problem is that if you try to do this, there will be, we are talking about, these are in picofarads, right? Very small. So if any wire or probe you try to do, that will have nanohenries of inductance, right? So it will start ringing. But what happens is that if you put a large R, it is a series RLC circuit. So if you damp it heavily, the L will disappear and it will just appear as a RC circuit, as simple as that. So we did that. We also matched this, with actual measurement. So that's how, and the thing is that students also do this. If you have the PCB files, then from the PCB files you can put it in Maxwell Q3D and you can extract the capacitances. So now how will you get the inductances? Now for the inductances also, wherever it is PCB, you can put it in Maxwell Q3D and you can get it. So that's one thing. But there is also this, right? Say for example, if you have a module, or I just said no, that the MOSFET, the terminals, they have inductances, right, which comes into picture. So if you don't know the internal geometry of the FET, you cannot put that in your, FEM simulation and get it. So that's how we have figured out some simple, that kind of test. Say for example, you want to know this inductance. So you keep one switch on and then you turn on this FET. So if you turn on this FET, both the FETs are on. This is a low voltage. So the FETs becomes RDS on, right? When they are fully turned on. So it makes a RL circuit. So now you just look at the step response of that RL circuit and try to figure out what is the value of L if you know RDS on well, right? So you can do this. So now we are, we have formulated the problem. So actually if you put everything, about 17 state variables you will get, I think. And then, these are, coupled nonlinear equations. They are nonlinear because these capacitances are nonlinear and the channel currents are nonlinear. Otherwise, circuit is linear, right? So hard to solve analytically, not possible, but numerically you can definitely solve, right? So now the thing is that this, what I just described, is a very complex way of doing this, right? You have to extract all this, put it in, and you have to make this, simulation and all that. So what does the designers are doing in the industry or in the other academic labs? So what people do is, see again I have here, this is, people use LT SPICE simulation. So many of the vendors will give you the SPICE model of the MOSFET. Right? So you can put those models, and then if you know the circuit parasitics, you can put those also here, and then you can actually see, during the turn on, turn off, how the output voltage and the current is changing, right? But this has two limitations. One problem is that, look here, by the way, if you actually sample 100 devices, you will see only 50 of the SPICE model actually works, right? And many new devices does not have a SPICE model in the vendor's website. This is one problem. And the second problem is that you see what I said before, what you can probe is actually this D prime, S prime points, right? Which are behind the inductors, right? And that is the voltage you can probe. And if you are measuring the current here, the current that you are measuring is not the channel current, because you have this displacement capacitors are there. At high frequency, the drain current is not the channel current. See, usually in our circuits, we always talk about drain current. We don't talk about channel current because drain and channel are same. But when switching happens, they are not same. Or, in the high frequency modeling of the MOSFET, they are not same, right? But why channel current is important? Because your loss actually is this drain source voltage multiplied by the channel current, and not this voltage multiplied by the drain current. So what you can measure here, because you are looking at the device as a black box, so what you are measuring is the voltage across those terminals and the current that is flowing through not just the channel but also on those capacitors.
And the blue plot, which current is that?
So this is the blue plot is this current. It is this current. It is the power loop current.
And you basically...
That is what you can measure.
Yeah. So first it's 0 because the lower FET is off.
Yes.
And then you turn the lower FET on.
Yes.
So the phase from 20 to 40 nanoseconds.
Yes.
Is that... Well,
so that...
Why is it flat in that region? Why is the voltage flat?
Why the voltage is flat, right?
Yeah.
So I will explain you this in another slide. You need to understand the dynamics, what's actually going on there. I will explain that. So, okay. So now this is one method that people do, and there is the second method that people do that is very popular in the literature. Everywhere people are doing that is called double pulse test. So what you do is you put together two FETs like this, right? And you sort of turn on this guy so that this acts like the diode, right? And you turn off this guy, I'm sorry, so that it acts like the diode. So you have that circuit here. And you basically, what you do is you don't continuously switch this. This is like a monostable multivibrator. You just give one shot to it. So what you do is you first, this is all off. Then you turn this guy on. This is the device under test. You turn this guy on. Once you turn it on, then actually this inductor charges through this loop. And the inductor current will keep rising. And once it goes to the operating point where you want to do the test, you turn it off, then you will get a turn off pulse, you will measure, and then again you turn it on, and when you turn it on, this time is very small so that inductor current will not change much, and then you can again turn it off and you can watch on these two. So because there are two pulses, we call it double pulse test. So what is the difference in this and the buck converter testing? Buck converter is continuous operation. So the loss will generate heat. And so you have to put the thermal there, right? Here you don't have to do that, right? So this is the most popular way of doing it today. But what is the problem with this? One is that you have to actually make the circuit. So now when you start, a designer starts making the circuit, there is a plethora of choice of devices available from XY vendor, and from X vendor also you have multiple series of devices available. How you know which one is better or which one you should use other than the cost, availability and all that. So to do that you need to do this calculation, this kind of calculation, and find out which one is better than the other for your particular use or specification, right? And so doing this, it is time consuming, and you can do this for only one device, right? If you change the device, the footprint of the FET will change. You have to redo the circuit and all of that. Anyway, but that's what people are doing right now. So the thing is that it took us a long time because we are not from the RF area. When we were talking about that course, I thought I will come and sit. But so the thing is that we try to learn. I think still we are learning. And all our measurements are at 10, 20, 100 kilohertz. So when we go higher, we were not that good. We have not been taught how to do these things. But these guys learned. So what we did is, so this is just the, what we used. So here, one thing we want to mention is that, we use that high bandwidth voltage probe, which is not isolated. The isolated ones were, the first generation that we had, the isolated ones were always slow. It is like, I think 50 megahertz around that, which can do, 1000 volt. But now you have this new probes, not new, now also 3-4 years from Tektronix. It's called IsoView probes, where you can also do very high bandwidth measurement, but still it is isolated. So we have those probes also now. And for the current, we use this coaxial current shunt. We put it in the power loop and measure. And the idea is that anything that you try to put there will increase the inductance in the circuit. That LDC will rise and your results will be different from what happens in actual converter. But the idea of the coaxial current shunt is that how the wiring is done so that it sort of cancels the additional inductance. So now here I will little bit discuss the question that you asked. So by the way, before I talk about this slide, I will tell you what happened is, so that's basically the story, right? What I just discussed, that is the research. Now I will show you some results there in a minute. But the thing is that, what happened with this is, before in the silicon era, which is still going on. 85% of converters are made with silicon till today, 85 to 90%, I think. But what happens is that the gate charge method or this linear scaling technique, which worked for IGBTs, it was very easy for the designers. You do an Excel, you collect the data and you put it, you close form calculation, you get the numbers. So what we tried at the beginning is that you have all this nonlinear dynamics going on. Can I simplify those dynamics and sort of solve those differential equations and get a closed form solution? And in this process, we found out that before FEM came 30 years ago, we had not been able to actually solve many nonlinear equations, and people did a lot of work on figuring out how to solve nonlinear differential equations. So we were able to solve some of this in the turn-on process, but turn-off we gave up. It didn't work. So in turn-on, I'm just showing you this thing. So what happens in turn-on, I will just go over and also explain that flat thing. So what happens is that you see it is turn-on happening. So this FET is actually off. So that means this current is actually flowing through this diode. Correct? So everything is DC and there is no current here, and this voltage is equal to the DC bus voltage because the diode is conducting, right? So now what happens is that the moment you turn on the gate here, okay, so what happens is that till the gate voltage goes to the threshold voltage is cut off, right? That FET is cut off. Till it goes to the threshold voltage, right, channel current does not change. So nothing actually happens in this circuit, right? So if you see, this is where the green is the gate source voltage of the FET that is turning on, and this is the DC bus voltage it is blocking, and the current through the FET is 0, right? Now what happens is that here, once it goes to, so after that, once the threshold crosses, right, you have still a large drain source voltage across it. So the FET is actually in saturation region, right? You have a large voltage across it and the FET is in the saturation region. So when you are in the saturation region, that time the gate source voltage, the channel current is only function of gate source voltage, typically, right? That is your square law, right? So there what happens is, as the gate source voltage starts increasing here, the channel current starts rising. But here, if you see this, till the channel current rises beyond I naught, right? If you look at KCL at this point, this diode will keep being on. And that is why if this diode is on, this voltage is clamped. So that is what is happening here. This voltage is clamped and this current is increasing. And that is why you see that plateau here. Now there is a little drop here that you can see. And that little drop, what happens is that somehow how it turns out, this is almost linear. So if this current rise is linear, if you look at this loop, right, diode is conducting, here you have a DC voltage, and what is happening is that across this inductors, you are also applying a DC voltage, right? So if the current is linear across an inductor, the drop is constant, right? And that is the drop across it, right? So that is a little bit of that explanation what is happening. But we could not do this, beyond turn on. So now I'll take another 5 minutes and probably close this. I'll show you some results and then. So then how we figure out what we are doing is right? So this digital twin is our simulation model. I know the FETs, so from the parameters from the datasheet of the FET, I feed it to this. Then here I have circuit that I have made. I measure the circuits and I feed it to this. Now my model is complete, right? Now you can also do SPICE. Take the model and put it in the SPICE simulation from the vendor and also feed the circuit parasitics to the model. And you do double pulse test, that is the experiment, right? So you got this 3 arm here, and we would like to see where each other stands, right? Now the thing is that what is observable or measurable in the circuit is the drain current, not the channel current, and the apparent drain source voltage, that D prime S prime, right? So the question is that can I match all 3 on that? So here is a plot. You see this is a this is a double pulse test, and we have used a 30 ampere device, 1200 volt from this is from Cree, I think. And you see this dot is the simulation, that is the developed model, and the continuous is the experimentally measured. You can see that this is turned on, so the DC bus voltage went from 800 to 0 in about 50 nanosecond, and the current increased to 0 to some 30 ampere in about 20 or 30 nanosecond, right? And you can see that both in turn on, turn off, we have a quite good match, right? So it tells us that the model is right, most likely. All the parameters that we have measured, the circuit parasitics, they are correctly measured, and the parameters that we have got through curve fitting from the datasheet are also accurate to a certain extent. So now this is probably the last slide that you would like to look at bit carefully. So now I am saying that my simulation model is my benchmark when I am actually measuring the loss, that is integral of actual drain source voltage and the channel current. And what you measure in double pulse test or in your SPICE simulation, which is the black box model of the device, and you are only probing the outside of it, you get the drain current or the IDC current and the apparent drain source voltage, right? And obviously these two things are not same. So if you now compute error, forget the analytical for a moment, you look at this is experimental and this is SPICE, the red and the green. Both are doing the same thing. One is happening in simulation, another happening in experiment, black box, right? And it is expected that their performance will be similar, and that is what you see. The green and the red or the brown are same. What about the gate charge method, the classic gate charge method, which does not take into account all the parasitics and all? Not there. Even though the errors are very high, it doesn't match. And then lastly, the analytical one is for turn on, we have been able to simplify the dynamics like what I was showing. And of course, it is simplified, it is not accurate. So with respect to the actual simulation, it has got error, but error is minimal, that you can see. But the problem is that we could not do this analytical and carry it on for other situations like turn off and soft switching and all that. There are more. So now one question that people asked us that, look, everybody in the world is doing double pulse test. Are you saying they are measuring incorrect? That's not true, right? So what is going on here? So here I will also answer this hysteresis about the capacitor question. We have a paper on that. So actually, if you write down your actual loss, E on, E off, you can actually mathematically, you can write that is the apparent loss plus something, right? And even if you don't look at this, see, look what happened here is, I am just looking at these terminals instead of this terminal. And I have, drop across the inductor and also current flowing through the capacitors. Now they do not store energy, right? So if I add turn on, turn off, because no energy is lost in the capacitor and the inductor, that should match. And that is what you see here. This is the half Li square, and this is the what you call energy-based capacitor, because it is not linear. So if you add them, the turn on, turn off will match. But where it will not match, there are many places this will not work out, right? Like one of the thing is that if that capacitor has hysteresis, the way when the voltage grows from 0 to 800 and when the voltage goes from 800 to 0, if the capacitor curve is not same, if there is a hysteresis in that, there will be a loss there. And we have a paper on that, and then, but you don't see that in low frequency. I mean, for us, low frequency is tens of kilohertz. If you go like hundreds of kilohertz, high frequency, close to megahertz, you are going to see that effect. So they will not really cancel, right? Now, if you look at this inductive component of it, look, if it is a buck converter, turning on, turning off, let's say, right? The current at which turn on happens and the current at which turn off happens are not same. So half Li square may not cancel if you have a large ripple. And then there is, I will not go into that, there is something that we call soft switching, where we achieve some lossless switching, where we do not do hard turn on, it is only turn off, right? So there also it doesn't work.
I mean, you also in the buck converter have dead time. In the dead time, you use the lower body diode, which is inefficient.
Correct.
So you try to minimize it, but you can't put it below a few nanoseconds.
Yes, absolutely.
But that wouldn't be included in here because you actually have more than 2 switching events. You have 4 switching events.
Correct.
So you go into body diode, then you go out of body diode.
So, Professor, I'll just maybe I'll just quickly explain it to you. See, there is only 2 switching that you need to, because
yeah, I know, but the buck converter has 4. Well, you have
4, right?
You have 4 moments.
Four moments, yeah, right? 4 moments.
Into that time, then you are in that time.
Then
you switch the other, then you go back into that
correct.
time, and then you go out of that time.
Now, out of that 4, you have to take only 2, because I'll just tell you. Say, for example, you switched from here to the diode,
yes,
and then this guy turns on, and
but the diode has a lot of loss during that time.
This has conduction loss. There will be conduction loss. The diode drop is higher, right? But when you now switch to the FET, which is now going to conduct in the reverse direction, then that turn on transition is lossless, because already the diode is conducting. The voltage is very small across it.
Well, it depends on the buck converter. I mean, the challenge what we are thinking about is converters which go from 12 volt to 0.5 volt. So converters which go to very low voltages. And then, of course, this is a big hit. 0.7 volt is a big hit if you're at 0.5.
Right.
And so,
yes.
So that's the direction we are thinking on converters which basically have very high current, very low voltage.
Right.
8 volt, 500 amp.
Right. We are also working on those.
It's for chip, local supplies.
Yes.
Is there any new idea how to make them, or are these all buck converters? I mean, if you go from 12 volt to 0.5 volt, inefficient.
So the thing is that you do not do that. So you can do two-stage, right? You can do a switch capacitor, and then you can do an NLC. So we are also working on that area. So on our circuit side, right? But you are absolutely right. It will be very inefficient if you just do 12 to 1.
Oh, that's
correct.
On-off ratio is 12 to 1.
Yes. So I think I am close to the end of this. So I think I told you all this story, and seemingly it works. So I will skip all this. And then what we have done is that my student is doing a startup on this, that we have a Python-based code for this, the model. And we are using also the AI tools, so that the designer has to just give the part number. So our tool will go fetch the datasheet in the background. It will do, all the cuff fitting and give you the numbers. So all you have to give is specification and what device you are looking at. So it will do all that, right? So that's something going on. And I'll just talk about this project very quickly. This is one of the application of this. So actually, see, in India, I don't know if you have been in India. So in India, two-wheelers are big, right? Because we have narrow roads and everybody wants to go fast. So two-wheeler is the thing. So now the thing is that if you look at the total EV penetration today in India, it is about 5% of the all vehicles on the road, right? And among them, if you see that 5%, if you take that 5% at 100%, then two-wheelers are about 80%, right? You see what I'm saying, right? Two-wheelers are about 80%. And if you look at two-wheelers, now two-wheelers also comes in varieties, like this is scooty, right? This is like 100cc something, and then it goes to 150cc, 200cc, then it goes to designer bikes and all that, right? But right now, the little one is the one that is getting electrified because of many other reasons that we may not be able to discuss now. So the Ether is a startup. It was a startup. I think no longer it is a startup. I think they have done an IPO now. So they were doing this two-wheeler. Now what happens is that inside the two-wheeler you have a 3 kilowatt-hour battery, which can take you on a flat road about 60 kilometer mileage it will give you. Now this 3 kilowatt-hour battery, so it is like that their concept is like laptop. So the charger is portable, and it is not part of the bike or the scooty, right? So right now what they do is they give you a 700 watt charger, which is about 2.5 liter and about 2 kgs, 2 to 2.5 kgs, pretty heavy, and it is 700 watt. So 700 watt, if it is 3 kilowatt hour, it takes more than 3 hours. So basically it takes about 4 to 5 hours to charge, right? And then if you go to our city, Bangalore, there are all the there are many EV stations are there, where charging stations are there, and also in the malls or different parking lots, people have also installed high, we call it DC fast charger, which is like of maybe this size, maybe this big, wall mounted. And that takes you about 1 hour, because it is 3 kilowatt hour, and 3 kilowatt if you charge, you can charge it in 1 hour. Still 1 hour, somebody is on a scooty is not nice, right? You have to find out where is that, then you go stand there for 1 hour and do it. So the question is that, is it possible? So essentially it is a 230 volt 50 hertz, like your laptop charger, you connect here, and there is a 48 volt battery on the other side. So now the thing is that how about actually we make that 3 kilowatt big charger into something of this size, and maybe 1 kg or less than that, so that it is so portable, you can put it in your backpack and go wherever you want. You can plug in and charge, like what we do with our laptop chargers. May not be that small, but still small enough of this size. So all that we discussed, right, about that gallium nitride and silicon carbide modeling and all that, right? So we have learned a lot of things, and we have learned how to use or how to minimize the effect of parasitics, do a proper design using our tools. So we have been able to actually make gallium nitride based charger, which is actually less than 1 kg and of this size, right? So which turns out to be a power density of about 40 watt per inch cube. And I think other than Infineon reference design, I do not know of any product which has been able to reach this, right? Where we are switching the AC-DC rectifier at 400 kilohertz. EMC is a problem. We have still not solved that problem. We have to work on that. And the thing is that, and the DC-DC is switching at half a megahertz, and we use their dual active bridge, and all our research we put into that. And right now there is a startup incubated on this in the campus with some ex-Ether guys. They have come out and doing this. So that this is basically the result, and you see, another thing I would like to tell you is that we are actually started seriously looking at this EMC side, because you guys work. See, the thing is that by increasing the switching frequency, we have made, this is the, there is a buck converter there, or what we call a boost converter there in the, in the AC-DC section. And this is the inductor that is big there. And that is the, the weight and all that, right? The GaN FETs are actually not much going on with them. So now the thing is that they have shrink to this, and look at my EMC filters. They are big, right? So we really need to do something there, and something we need to bring out to solve this problem. So we had some discussion with Bibu and Professor Yan about this, and if we have to go commercial on this, or for this technology to happen, we need to figure out how to do this, right? And I don't think we have not done any test with LISN. This is like a first cut 2-stage EMC filter design with that coupled choke and Y capacitors. We have not tested yet, so that's an open problem, and we need your help.
Well, it depends, of course, a lot on how much ringing you have. So you have two classes of problem. You have the class of
yes,
and then you have ringing, and the ringing is, of course, depends on the loss mechanisms. Which
correct.
But the ringing will be for that circuit maybe 20 megahertz, 30 megahertz.
Yes, you are right. It is about 20 to 30 megahertz. I will go. Yes.
And the ringing, I mean, this ringing, of course. One would have to see what type of EMC problem dominates. This can be, at a gigahertz. It can be the ringing. It can be simply harmonics. One can look at the coupling pairs. The two inductors would sit like that. They will strongly couple to each other. They will partially not useful anymore.
Okay.
And for the ringing, one would have to see what are the loss mechanisms. Of course, you can always put a snubber there, then you lose some efficiency. But,
yes, Professor, we don't. Exactly right.
But one would have to first analyze it. There's no way from a photo to say what the problem is.
Yes, absolutely. Unless you measure and model it, you don't know, right? What is this? But the good thing is with our model, we can, if we know the circuit as you have seen, we can predict these ringing frequencies and these DVDTs and all that.
Frequencies are relatively easy to predict because that means you need the loop inductance.
Yes, you are absolutely
but
right.
The attenuation of the ringing is extremely difficult to predict.
So now I'll tell you, we are now working on this modeling stuff we have done. Now the second stage is we are working on some active mitigation techniques, right? So I may just tell you this, in the institute we have a gallium nitride fab and we have a full packaging line. So we have some active solutions that, you cannot put those active solution on the board and sort of do the PCB level design to solve this kind of problems. So, but we are working on that and see that whether, we can do a packaged some solution that we can package with the devices and the drivers. That's one way of looking at the problem. But unless, as you rightly said, unless we exactly understand where the problem is, or have the correct model, we do not know how to approach that. Yeah. Very interesting.
Yes. I mean, that's certainly something we can work on together.
Yes,
I mean, that's
absolutely.
Falls in our domain of expertise to make it worse. Sorry, to make it better. When I look at your photo, what I would worry is that you will never pass vibration test.
Oh, this one, no, right? I know.
I have to take this. Sorry.
Sure, please. Okay, all right. I think I have come to an end. Maybe you can ask question. Thank you. Thank you for your attention.
Yeah, sorry, I was late, but the previous thing, so it's that you didn't do any EMC tests.